Hello everyone, my name is Hyung-soo Kim from New Energy Business Department of KEPCO. First of all, it is a great honor to win the 5th ISGAN Award of Excellence. On behalf of KEPCO, I would like to extend my thanks to all of you here. Then I'll give you a presentation about the success story about the KEPCO Open Microgrid project. Next. Let me start with the project background and implementation. Next. I would like to advise that the project had been developed to aim to achieve 3 main goals, like helping to mitigate climate change, easing variability of renewable energy, and improving flexibility and reliability of power grid. Next. As shown in this table, there are around 430 inhabited islands where 30,000 reside, and 127 of those islands are currently being supplied power by diesel generators. However, social needs such as carbon CO2 emission reduction, expansion of renewable energy, and cost effectiveness triggered the project aimed at developing renewable-based microgrids to facilitate active energy production and consumption in a community unit. I therefore can tell you that 127 diesel power plant leases have come to end in sequence. Next. This is a brief outline of the project. Korean government and KEPCO co-invested $25 million in the project, whose duration was 36 months, and that the target was to facilitate the transition to cleaner and smarter energy. Gasa Island and Sinan district was selected for project site. Their population are 330 and 42,000 respectively, and the main industries of both Gasa Island and Sinan are agriculture and fishery. The electrical system for Gasa Island was comprised of 300 kilowatt diesel generator and 2 low voltage distribution lines, while Sinan has 2 megawatt PV and 3 megawatt wind turbine connected to 3 high voltage distribution lines before the project. Next. Let me talk about the MG system, EMS, which stands for Energy Management System. Key component of standalone MG is specifically used to forecast load and renewable energy output and battery state of charge management. Inverter is designed to keep frequency and voltage in relative range, and then PCS is aimed at helping control active and reactive power in case of shortage of rating. Lastly, water pump and air conditioner in the battery room are used for pseudo load in the event that the surplus energy is produced. Next. The main purpose of grid connected MG are to increase the amount of renewable energy like as PV, wind turbine, and ESS connect to the grid by optimally regulating voltage and automatically restore the power grid by leveraging DMS, which stands for Distribution Management System, and enables self-healing technology and dynamic islanding. Next. Next, let me mention the project outcome. Next. The EMS aimed at compensating for the variation of the load and renewable energy output serves to improve the power quality and operational efficiency. Active distribution system is designed to help the power grid to accommodate more renewable capacity and improve the reliability. Lastly, the project has favorably impacted the domestic electrical industry growth, like the manufacture of distributed energy resources and distribution intelligence electronic devices. Next. In terms of economic rationale, the project has brought about a great value by reducing cost of energy. Analysis of the fuel cost savings shows that the average fuel cost for 11 months from the commercial operation date was reduced by 81% compared to the same period of previous year. and the operating cost was curtailed by $0.1 million per year. Next. KEPCO has transferred the technology it has developed itself, and it is valued at $0.6 million to local suppliers. On top of that, 13 domestic and 5 international patents were registered. Eventually, this has laid groundwork for creating policies to promote the expansion of MZ for other islands and create over $170 million of economic impact. Additionally, the success of the project has led to exporting the MZ model to overseas markets like Mozambique and Canada. Next. KEPCO has achieved 350 world highest level of renewable energy capacity installed per peak load, as well as capacity level of its distribution feeder to accommodate distributed energy resources up to 6% compared to permissible maximum capacity. Outside of that, we have attained 100% world-class constant voltage and frequency maintenance rate. As you can see in this graph, the frequency regulation rate of inverter with renewable running goes up to 100%. Next. Now let me talk about the next step. Next. The first thing we are currently planning is to extend our energy abroad. To this end, we make sure that the business model is strategically produced by reflecting requirements and needs of the country we are targeting. Economical energy model is designed to give light and power to the people, not experience electricity yet, in the developing countries. For the reason, economical energy is very simply configured with PV and ESS, not including state-of-the-art technology like EMS. On the other hand, advanced model is aimed at helping island or remote area supplied with power from conventional generation to be energy self-sufficient or carbon-free, and consists of cutting-edge technologies like GMS and grid-connected energy to target developed countries which want to enjoy the benefit created from the high power quality and improved reliability. In addition, we are currently working to develop power-to-gas-based energy designed to convert the surplus power from renewable to gas fuel. Next. Let me level this presentation by explaining alignment with ISGAN mission. Next. In terms of developing smart grid ecosystem, Korean government established the National Smart Grid Master Plan every 5 years, while stakeholders actively get involved in the whole process. In sync with them, KEPCO is investing in smart grid development with a strong drive from its CEO. This is the way we move smart grid ecosystem forward based on the ISGAN mission. Next. Thank you for listening. If there is a need for further information or clarification, please feel free to ask me.
Great. Thank you very much.
My presentation comes to end.
Yeah, thank you very much for your presentation. Then I think we can now move to our next presenter. Mr. Hyung-Soo Kim will have to leave us in a few moments, but his colleagues will be able to go through questions and answers afterwards.
I believe that like Mr. Chair and Mr. Chu will ask any question you have.
Exactly. Mr. Chu will be able to go through the questions. Yeah. Thank you very much, Mr. Kim. It was a pleasure having you today in our webinar. And, let's be in touch for future opportunities. Thank you very much.
Okay. Thank you for having me.
Thank you. Now, it's goodbye, Mr. Kim. Now it's time to Bartłomiej Arendarski from Hofer. Bartolomei, the floor is yours. You can quickly introduce yourself and go ahead. Thank you.
Thank you, Fernando, for the kind introduction. I'm Bartolomei Randarski. I'm with Fraunhofer Institute for Factory Operation and Automation, IFF, in Magdeburg, Germany. And I would like to introduce you our project RIGRID, Rural Intelligent Grid, from vision to realization. This project is a part of the ERANET Smart Energy System family of projects. We would like to thank European Commission and Union for supporting us in the frame of the Horizon 2020 program. Let's start the presentation. Okay, what motivates us to implement the RIGRID project? So as you know, the renewable energy sources are playing more and more important role in the power system. However, it is not easy to integrate them from the technical, economical, and from the social point of view into the power system. As we know, the aim of the European Union is to have 80% of the total electricity demand covered by renewable energy sources in year 2050. So we have a very challenging aims, and how to do it. As we know, the opposition of the local communities for implementing and integrating renewables, it's high in Europe, and not only. So there's this typical NIMBY effect. So I'm for renewables, but not in my backyard. So how to overcome those problems, and why we focus on the rural regions. As you know, the most European areas in Europe are rural. You can see it from the graph on the top. The most regions are marked with the green color, and they are rural regions. Also, there is a more place over there for integrating, for example, big wind farms. And as well, the rural regions are less invested in compared to the urban regions, so they have a more potential for big investment now, as well as the reliability and security of supply in the rural region is lower than in the cities. So Rural Intelligent Grid project was implemented in Germany and Poland. Here you can see the consortium of our project. I think it's a very good mix of the research institution like Fraunhofer Institute, IFF like Academy, Warsaw University of Technology, the industry like Electrum, company from Poland, European Copper Institute in Poland, as well as Renewable Kraftwerke Harz, and the association like Harz Renewable Drüberg. So as you can see here, the project was implemented in two regions, municipality of Dadersheim in Germany, which is well known as a city of renewables. Already 80 megawatts of wind power are installed in this small town and 2 megawatts of the photovoltaic, and they are supplying whole region with renewable energies. They are very successful in investment in these technologies because they develop kind of business plan involving the inhabitants in this kind of projects. And this knowledge and experience we would like to share in the RIGRID with the municipality of Puńsk, which is the region in the eastern part of Poland, a very rural region where some investment in renewables begins, but we want to show them the good pathway in order to accelerate this investment. So the objective of the RIGRID project is to integrate RES, renewable energy sources, into the power system, to share the technology from the good practice, to integrate renewables in the regional level, and to motivate the investors and users and residents for these smart green solutions. Many methodologies were used in developing the solutions of the RIGRID projects, and as a main result, the interactive energy and infrastructure application for optimal planning and operation of the energy infrastructure in rural areas was implemented successfully in two areas, in Dadersheim, Germany, and in Puńsk in Poland. So shortly, I would like to show you the three main layers which we address in the RIGRID projects. Actually, I would like to go back to the one slide which was not shown. As you can see here, the RIGRID project addressed all three layers of the ERANET Smart Energy System initiative. So it's a technical layer, social layer, and economic layer. We know many projects which are pretty focused on the technical solutions. However, we cannot forget about the economical and social aspects as well. So the technical layer was addressed in form of the improvement of reliability and security of supply and reduction of CO2 by integration of renewables. The social layer was addressed while increasing the acceptance of the renewable investment in rural regions, also creation of new jobs and opportunities for the inhabitants of these regions. And the economic layer was addressed via developing of the tool for optimal planning of and choosing of the optimal technology for the particular region, as well as increasing the visibility of the regions. So shortly, the results of the technical layer, so the concepts and methods, algorithms for optimal planning and sizing of the microgrid infrastructures in the rural regions were developed based on the software solutions. The demonstrator in Punsk was integrated. You can see it on the bottom left picture. It includes of the wastewater treatment plant. It's a small-scale demonstrator with 30 kilowatt consumption, photovoltaic of 40 kilowatt peak, and diesel generator. Also, the battery storage was integrated in frame of the RIGRID project. Some controllable loads, measuring technologies, protection, and communication were implemented. On the right bottom side, you can see the EMAX, which is the Energy Management and Control System developed by company Electrum, which was successfully integrated in this small demonstrator for optimal monitoring and controlling of the whole system. And now it's commercialized and it's operating in many photovoltaic parks in Poland. And on the top right picture, you can see the approach for the net zero energy system of Punsk for 2050, which I will elaborate on it later. From the economic layer, we have developed the business model evaluation tool, which is based on the 6 steps, beginning from the identification of the business model, evaluation of total investment cost, evaluation of the benefits during the lifetime, also evaluating the net present value, and if net present value is bigger than 0, then evaluating of the internal rate of return, up to the comparison of the internal rate of return for the identified business models in order to choose the optimal business model for this particular situation. Oh, the slides are jumping faster. So the third layer, which was addressed in the RIGRID, is the social layer. As you can see here on the pictures, we have developed a planning tool which include the virtual reality technology in order to visualize the future scenarios of integration of renewables, microgrids, and storage in the rural regions. Why we did that? It is because many people are afraid about the new investments in the region, basically in the rural regions. Erecting new big wind farms or photovoltaic parks, it's not always acceptable by the inhabitants. They are afraid what is coming, how it's going to look like, how they can live with this infrastructure in the neighborhood. And with the virtual reality technology, we are able to visualize all scenarios which can be imagined in the future in order to show the audience how it will look like in their environment. And in this case, we bring the level of fears and the level of fact. So we can see if the infrastructure will be visible, if it will have an impact on my, for example, area. And in this way, we can easily discuss many cases to find the optimal pathway for the microgrids, for the overhead line, for the cables, for the new generation units, and to find a better solution and to accelerate and increase the investment process. We have integrated these solutions in the 2 regions, and in the RIGRID project we have tested 6 showcases. which were demonstrated for all parties involved in the projects, for the engineers, for the investors, for the companies, also for the inhabitants and the municipality. One of the showcases is the analysis of the net zero energy system Punsk 2050. So in this case, the district was analyzed, all the buildings were analyzed, parameterized, and modeled. The area was analyzed in order to find the places for the implementation of renewables, choosing optimal technology, also storage, battery storage system sizing applications was implemented, and placement of the storage in the microgrid. And in this way, we will be able to develop the net zero energy district. As you can see, the net zero energy district holistic approach for Punsk is shown here. So because we want to integrate as much as possible renewable energy sources, the approach is showing that all the consumption will be based on the electricity. So as input, we have the electricity from the renewables, and we are using it for lighting, for heating, for electricity loads, and also in the future for the mobility, so which means for electric vehicles. And you can see the model was implemented in the professional modeling tool, including the multi-energy system, so electricity, heating and cooling, and also mobility. As a result, we can see here our calculations. So for the very small town of Punsk, we have tested the mix of the photovoltaic and wind for fully net zero energy system. And you can see with the light green, they are marked the two lines from the bottom. So we can see that the optimal share is 2 megawatts of photovoltaic and 5.2 megawatts of wind, as well as 1 megawatt and 5.8 megawatts of wind. Then we have a levelized unit energy costs are the lowest. So the costs of the investment and of the operation for the generation units are the lowest, 61 and 51 euro per megawatt hour. Also, the net present value is presented, and the internal rate of return is the highest for these two scenarios by 7.9 and 8.2%. Of course, that you can make a question if the using electricity for heating is economically valuable. As we can see here, using the average values for Germany houses and weather typical for this region, the net zero energy system using for heating, the costs are lying by 14 euro per square meter, and this is the pollution-free solution. So in compared to the natural gas, oil, or the biomass pellets, or the district heating, which are a little bit lower, but they are also by beginning from 9.5 euro per square meters up to the 13.5 euro per square meters. The costs for the net zero energy system are not that much higher, and we have to not forget that this is a pollution-free solution. So very, very good for the air and for the future development of the society. And now I would like to show you a short video representing the results of the RIGRID project integrated in Dadersheim and in Punsk in Poland, in order to give you some impression how it looks in the reality. Thank you, Fernando, for starting the video. As you can see here, we have a Punsk region, which is very rural. It's a very beautiful area in the northern part of Poland. It's called the green lung of Poland. So it is a very touristic and very green region. Mostly people are living there from the agriculture. So they are focusing the typical problem that the people are leaving regions, moving to the cities in order to find new opportunities, and also the investments are needed in those regions. The security of supply is not that high in this kind of regions, mostly because of the weak structure of the power system, and that's why the possibilities of integrating of the microgrids is a very promising solution for those regions. We have also some economic factors which motivate us to integrate the RIGRID project in this region, as well as the social issues which are very challenging for this kind of regions in order to create new jobs, to keep the people in those regions, and also to bring new people in those regions. Here you can see again the consortia of the project. And compare, we have the Gasa region in Germany, which is very successful already with the integration of renewables. As you can see, the big wind farms are integrating renewable energy in the power system in the regions. Also, the solar panels are integrated in these regions. These regions is characterized by very high penetration of renewables. They are supporting whole region with the renewable energy, and also exporting many times in the year the renewables into the main power system. And also this very great experience of Gasa Island was the backbone for the implementing this kind of solution in other regions, in this case in Puńsk region. As you can see here, there is a water treatment plant in Puńsk, which already has 40 kilowatt peak photovoltaic power plant supporting the process of cleaning, and also diesel generator as a backup source for the case of the blackouts. As you can see, the system is already well communicated with the ICT technology. In the RIGRID project, we have supported the system also with the battery storage system, which you can see now, in order to also operate the system in case of disconnections from the grid, to also support the islanding operation, and also to store the oversupply of photovoltaic during the day or the night time of the consumption of the power plant. As you can see here, all the buildings were modeled with their heating and cooling performances. Consumption profile were built for the whole Puńsk. The many scenarios of integrating renewables were tested, of locations of photovoltaic parks, of wind mills in the region, also on the small rooftops photovoltaic, which are already now finding place in the Puńsk. The EMAX energy management and control system developed by Electrum was integrated in the demonstrator of Puńsk. As you can see here, also on the control room, the remote access to the whole microgrid is possible, so the operator can make monitoring and also control functions from far away. Actually, the control room is located 250 kilometers from Puńsk in Białystok, where the headquarters of Electrum is placed. And you can see this is very good for the operator, that not only the possibility of controlling on the place is possible, but also remote, so they can save time and the service money in order to operate the system. And this is the short overview of the results of the RIGRID project. This communication and dissemination process was coordinated by the European Copper Institute in Poland, Wrocław, with the help of Michael, which also bring us to success of disseminating the results of the RIGRID project, and also was a part of the success of winning the ISGAN Award of Excellence Runner-Up of 2019, which we would like to thank to the all partners and the audience. And I'm happy to answer your questions which you will have regarding the RIGRID project. Thank you.